Where do you see that? Oh, I see it. Right there? Okay. All right, so we're gonna look at acid-base titration. The nature of a titration is that you have something in a burette that has known concentration. It is known as your standard solution. It is known as your titrant. T-I-T-R-A-N-T. That's a titrant. You let a certain amount of volume out and you agitate, typically an Erlenmeyer flask. An Erlenmeyer flask, if y'all recall, looks like that. The reason we use an Erlenmeyer flask when we titrate is because the neck is narrow. The tip of the burette fits inside the neck and it doesn't allow things to splash out. Okay? So you have a burette tip that is depositing some known solution of known concentration into the Erlenmeyer flask that has a substance of unknown concentration with an acid-base indicator typically. What's in the burette can be acid or base. What's in the flask can be acid or base. But if what's in the burette is acid, what's in the flask will be, and vice versa. Okay? The lab that you do tomorrow will have base in your burette, and you'll have two different acids that will be in your flask. The contents of the flask are known as the analyte or the titrand. That word's not used very often, but it's in something that I saw recently. So this is your titrant. I can't spell. Good grief. And in the analyte and titrand, we have an indicator. And an acid-base indicator is present to indicate an end point that should equal what's known as the equivalence point. So ideally, an end point and an equivalence point are the same point. You had a redox indicator in a lab that you did earlier in the year. You had some potassium dichromate as your titrant. You had a ferrous sulfate solution as your analyte. You had the redox indicator in with the analyte. Y'all recall doing this? You added titrant, you swirled it, you added titrant, you swirled it, you added titrant, you swirled it, you saw it turn green. You knew that that wasn't the end point of the titration. The end point is when it turned purple. And then you recorded a volume at that end point. In an acid-base titration, that end point should be called an equivalence point. That is where you have equal moles of titrant and analyte. The equivalence point is where we have equal moles of titrant and analyte. Mm-hmm. Okay, so what we do with an acid-base titration is we have three scenarios. We can have a combination of a strong acid and a strong base. We can have a strong acid and a weak base, or we can have a strong base and a weak acid. We do not typically titrate a weak acid, weak base. You don't usually see that. What I asked you to watch during lunch was a titration that I made up of strong acid and strong base. That is what you're gonna do as your first set of titration stuff tomorrow. Did anyone watch what I asked you to watch at lunch? Yeah, okay, so some of you know what I'm talking about with the titration curve that's established. A titration curve has lots of important information on it that we'll talk about as we get deeper into this, because we've got to do buffers after we do this. Okay? Buffers are like my favorite problems on earth. They're just awesome. Awesome, awesome, awesome. All right, so what I aim to do is work hopefully one of each of these types in class. I did a whiteboard video on each of these types as well. Okay? I'm making this up on the fly. You know what that does. All right. So let's do some KOH. What did I do in the whiteboard video? Hello, guys. What did I do in the whiteboard video? NaOH and HCOOH. I don't know what I did. HCl?
Yeah,
HCl. Okay. Let's do KOH and some HNO3. How about that? KOH and HNO3. Y'all agree those are both strong? What happens with the strong substance? Okay. So we know because we have a list of strong acids and a list of strong bases, that those are strong, and anything that's not on the list is weak. All right. We're going to make the KOH the titrant. So we're going to know its concentration. And let's make it, let's see, tomorrow uses 0.1. Let's make it 0.25 molar. Okay. And we're going to have the HNO3 be the analyte. And what we're going to do is know the concentration. Isn't that what I did in the whiteboard video? I did the concentration of both, didn't I? Okay. And we're going to see where it takes us. In tomorrow's lab, you're not going to know the concentration of your acid, and you're going to use a pH probe, and you're going to gauge its pH at certain volumes. Okay? If you watch the whiteboard video, you had pH in the graph on your y-axis, and you had volume of titrant on your x-axis, and that's what makes a titration curve. Okay. All right, so let's make this thing 0.1 molar, and let's have 10 milliliters of it. We okay with that?
Do you always know the volume of the analyte?
You know the volume of the analyte. Yes, usually that's what you know. We're going to change that to 0.4 molar. Just made it an easy change if that's okay. All right. So what I'm going to do is a series of calculations at different volume points. Okay. And what we're going to do is calculate the pH at different volume points as we go through it. Our volume points are going to be 0 milliliters of titrant. These are volume points of titrant. 0 milliliters of titrant. And then we'll do 5 milliliters, 10 milliliters, 15 milliliters, 20, 25. Okay. All right, I'm gonna erase what's over here and I'm gonna end up putting, this is gonna be volume of KOH. This is gonna be pH. And I'm gonna make a list over here of my pHs as I work through my problem. All right, where's my eraser? My eraser. I use different thingies when I'm on PowerPoint and I get confused as to where everything is. All righty, so do that. I really want this to be over here. I really want this to be over here. Perfect. Look at that. Except I'm gonna need to erase stuff in a minute. All right, so if I have 0 milliliters of KOH added to my Erlenmeyer flask, all I have is what in there? The analyte, the acid in this case, okay? I know that I have 10 milliliters of, in particular, what do we know about the HNO3? 0.4 molar. So 0.4 molar means that it's 0.40 moles per liter, correct? And I'm gonna write that it's of H positive. Why don't I write that it's of HNO3? We don't care about the NO3 negative. The thing that we care about is the H positive, and we can care only about the H positive because this is what kind of acid? Strong. Okay. Notice my liters will divide out and it'll leave me with what unit? Isn't that fun? Millimoles are so great. And how many millimoles is it? 4 millimoles. Okay, and that's of H1 positive. This is a process we're going to go through for each one that we didn't have to go through for this one. And I'm going to show you why. But I would normally take this 4 millimoles and I'd divide by the volume, the total volume, get a concentration of H positive, and find my pH. Well, all I have is H positive right now, correct? So I can take 0.4 as my concentration of H positive, right? And if I know my H positive concentration, all I do is take opposite log of it. And that gives me my what? pH. How many decimal places should my pH have? 2, because I have 2 sig figs. Remember, these are the weird rules. Again, I just made this thing up, so I have no clue what my answers are. What do you get, Luke?
0.40. I don't
Luke, do you take the opposite log?
I did.
I got 0.397.
Good grief, y'all. You messing with me.
I got 0.397 and then I rounded it
Okay,
to
that's really weird though. I mean, like really weird. What's up with that? It is 0.398, which to
0.40.
Luke, I am just like stunned by this. Y'all, I just made this up. So our initial pH is 0.40. Wow, that is just bizarre.
That is strong.
Okay. I don't know.
I just put it in the calculator and said, no, no.
4 times 10 to the negative 1, right? So it's the log of 4 plus the log of 10 to the negative 1. Golly, okay.
That's accepted.
10 to.
I'm just accepting it. It is bizarre. All right, I'm not gonna erase that. Holy moly. Holy moly. Okay. I'm just gonna do my second one right here. All right, my second one tells me that I have 5 milliliters of, what was my concentration of KOH?
2.25.
0.25 what? Moles of what? OH. Why do I just care about the OH?
Do not care about the potassium.
Because the potassium is not, doesn't have acid or base properties. And what's that going to give me?
1.25.
1.25 millimoles of OH negative have been added. We okay with that? To 4 millimoles of H positive. Okay, what's the reaction at hand? The OH is being added to the H positive to get H2O. Initially, I have, 1.25 millimoles of OH ion. And how many millimoles of H positive, since I figured that out in the first one?
4.
4. Who's limiting?
OH.
Y'all okay with that? Because it's a 1-to-1 ratio that's present in the lesser amount. And acid-base chemistry is always 1-to-1, by the way. That's a nice thing about it. So my final amount is how much of OH? Yeah, because we just said it's limiting, so there's not going to be any of it left. How much H positive will be left?
2.75.
Okay, and that's millimoles, right? Sitting in a total volume of, careful with this, we had 10 mils of analyte, we just added 5 mils, so we have a total volume of 15 milliliters. Notice the millis will do what? Divide out, and it'll give us moles per liter, which is your molarity, your concentration. And this is going to be our concentration of whom?
H positive.
H positive. Notice I'm using 2.75, the final amount of H positive, divided by the total volume. And I get what?
0.183.
So 0.18. Let's do 2 sig figs. Let's pay attention to our sig figs in this. Molar, and that is our concentration of hydrogen ion. And if that's the case, what can I do now? Find the pH. I'm getting 0.74.
Yes.
Okay, what happened to my pH?
Went up.
It went up because I added what?
Base.
A base to it. We okay so far? Yeah, I'm gonna make a new page and we'll just come back to this one and keep adding to this list. All right, my next volume of titrant is 10 milliliters times point, it was 0.25
Moles.
moles per liter, didn't 1.250, right? 0.25, okay. And that's of OH negative. All righty, so how many is that? We're okay so far? We go back to our reaction that is H positive. Well, I did it OH first, didn't I? Plus H positive yields H2O. Again, we don't care about the H2O. We have an initial and a final because this is a stoichiometry chart. This is not an equilibrium chart. This is a stoichiometry chart because we're using millimoles. We're not using molarities. All right. How many initial millimoles of OH do I have? How many initial of H positive did I have? 4. Who's limiting? The OH again. How much of it will remain? How much of the H positive will remain? So then I take 1.5 millimoles and I divide by my new volume that is,
20 milliliters.
whoops, 20 milliliters. My millis will cancel out. I will get I'll get 0.075.
Yeah.
And that equals my hydrogen ion concentration. So if I take the opposite log of that, I get 1.12. Y'all agree? I'm not showing taking the opposite log, I'm saying it because we do it so much that you should just get used to doing it every time we see a hydrogen ion concentration. Is that okay?
Comments. I have a question.
Okay, hold on just a minute, Sophia. This 2.5 right here, right there, it's 2.5 millimoles of OH ion. Okay, Sophia, what's your question, baby?
I was gonna ask, and this is a really stupid question, but I was gonna ask where you got the 4 and the 1.5 from under the.
Or go back to your very first problem solving in this problem where we had 0 milliliters of titrant added and we established that we had 4 millimoles of hydrogen ion.
Okay, yeah.
Initially. The 1.5 comes because I'm not showing a change line here. My change line would read minus 2.5 minus 2.5.
Okay.
Is that okay?
Yeah, that makes sense.
All right. All right. So that's where the 1.5 came from. Okay, I'm going to go back and I'm going to put 1.12. Is that right? Okie dokie. Now we're going to do the same thing, but with how many milliliters?
I have a question.
Yes, sir.
What's the rule for significant figures?
However many significant figures you have in your concentration dictates the decimal places for the pH. Okay. All right, so what was my next volume of titrant? And again, it was 0.25 moles of OH per liter. Liters divide out. I'm getting 3.75. Yeah. That's millimoles of OH ion. Okay. I'm going to do another stoichiometry chart over here where I have OH negative plus H positive yields H2O. I don't care about it. I have an initial, I have a final, and there's a change in the middle there that I'm not showing. My initial OH is 3.75. My initial H is 4. Do you see how we're getting closer and closer to the OH not being the limiting reagent? Okay. So how much am I going to lose of the OH? All of it, because it's still our limiting reagent. So I'm going to have 0 of it remaining. how much of the H positive will remain? 0.25, and remember that's millimoles. So then to find my concentration of H positive, I take 0.25 millimoles and divide by my new total volume. You're not going to be asked to do this succession of calculations. You'll be asked to do a part of it. Okay, I'm just showing you different parts. All right, what's our total volume? Our millis divide out. You get 0.01.
I thought we were doing
Correct.
milliliters, right?
Say it again.
I thought we were doing 15. Oh, no, we're not. Okay, never mind. We just did that.
It's total volume. Yeah, so we have to consider what the analyte had as its initial volume. So we did 10 milliliters plus 15, 10 for the analyte and 15 for the titrant. Is that okay?
Yeah.
Okay. So what is our pH? Y'all ought to be doing this one in your head.
2.
So it's 2.0. Okay. Do you see our pH continues to go up, correct?
Yes.
Okay. All righty. What's our next volume of titrant?
20.
I can't do that math. 5.
Yes.
Okay. I have my OH negative plus my H positive equals my H2O. I have my initial and my final. I have 5 and I have 4. And now, who's limiting?
H positive.
H positive. What I've just done is bypassed the equivalence point because I couldn't do that math in my head. Okay? The equivalence point would be where we had what for H positive, 4, and what for OH negative, 4. And in that case, what would the pH be?
7.
7. Because it would just, what would be there? The only thing that would be there is water.
Water.
Is that okay? All right. All right, but I bypassed it, and we're going to see that when we graph it in just a minute. I bypassed it, and now I'm going to have how much H positive remaining and how much OH remaining. Okay. So now I can get the OH ion concentration of 1 millimole sitting in a total of
30 milliliters.
for a 0.33 molar solution, yes? Is it 0.033?
Yes.
Okay. And that's not going to enable me to get a pH, it's going to enable me to get a pOH, and then I can find pH. I get a pOH of 1.48. And how do I get pH from pOH?
14 minus
14 minus pOH, so I get a pH of 12.52.
Yes.
Okay, so let's look at what our data just did. 12.52. It just skyrocketed, correct? Okay, we got one more volume to do, then we're going to graph it. Do that one over here. We had 25 milliliters times 0.25 moles of OH negative sitting in a liter to get how many millimoles?
6.25.
6.25? Is that right?
Yes.
Okay. 4 was my initial amount of hydrogen ion. Who's limiting? Hydrogen. How much is left
2.2.
of hydrogen? 0. How much is left of the OH? Then I can find my OH concentration. Total volume is 35 milliliters. At 0.064. Is that correct? I get a POH of 1.19. Yep. And a pH of 12.81. Okay. All right, so I'm going to go back. Yeah, go here. 12.81. And now I'm going to graph. Okay. When I graph, I have milliliters of titrant on my x-axis, and I have pH on my y-axis. Okay. And you notice that my pH starts very low because I only have what initially? HNO3. So it starts real low. I'm not going to really graph this. I'm going to show you what shape it should make. It should do something that looks like that. And smack dab where it is the most vertical, whatever, is where the equivalence point should be. So graphically, we can get it. Is anyone in calculus?
I'm milliliters. It should be 16 milliliters. I think.
Oh, you've calculated what the equivalence point should be? Okay. I was just going to explain to folks who are in calculus, you can take the second derivative. Have y'all done derivatives? You can take the second derivative and where the line crosses the 0 will pinpoint exactly where that volume is. Okay. What do you know about the pH right here? It's 7. So that's a pH of 7. And the reason it's a pH of 7 is because this is a strong acid with a strong base, and its neutral point, its equivalence point, its end point is at a pH of 7. Okay? If I have a strong acid titrating a weak base, its equivalence point is not going to be 7, it's going to be below 7, because it's a strong acid titrating a weak base. If it's a strong base titrating a weak acid, its equivalence point is going to be above 7.
So at the equivalence point, it's like exactly, the slope is exactly vertical.
Yep. Yep, so 0.
Well, it's vertical.
It's undefined, right? Or 0. Which one?
Undefined.
Undefined. Which is undefined? Dividing by 0?
So with the strong base and weak acid,
It's going to be greater than 7 for an equivalence point pH. Correct. All right, so I have something else to say about this. An acid-base indicator that could be used for this particular titration is bromothymol blue. It's one that you're going to use tomorrow. Bromothymol blue, BROMOTHYMOL. Bromothymol blue is blue in a base and yellow in an acid. But the reason it's great to use for a strong acid, strong base titration is that it is green when it's neutral. Y'all get that? So tell me, in this particular incidence, what color is my analyte going to be with the abbreviation for bromothymol blue is BTB. So we're going to use BTB. And what did y'all just tell me?
Yellow.
So I know that my analyte is yellow to begin with. You okay with that? The KOH is colorless. As the KOH comes out, the analyte is going to turn what? And once it reaches its equivalence point and it's green, if I keep adding base, then it's going to turn blue.
Lots of colors.
Yes. Okay, what do y'all think about this so far?
This one.
Okay. How much time do I have?
10 minutes.
How much time do I have?
Less than 15 minutes.
Less than 15 minutes. Okay, I am not going to have time to work out a strong acid, weak base, strong base, weak acid, but I did whiteboard videos on them. Okay, here's my recommendation is you are working with a strong base tomorrow and a weak acid in addition to strong and strong. I want you to watch this evening the strong base, weak acid whiteboard video. Probably, how long was the lunch one?
16 minutes.
It's probably about the same. Okay? Y'all like?
This part.
Strong base.
It's like it's about to knock it.
Strong base, so tomorrow you're using some NaOH and you're using HCl for your first stuff. And then your second stuff is acetic acid. What do you know about acetic acid? Is it one of your strong ones? No, so it's weak. What's its common name?
AA.
HAC is how you abbreviate it.
Hack.
PAC. So, hold on one moment. Jeannie, see if you can smell through your mask. Take the mask off. No.
Sulfur.
What's acetic acid commonly known as, Ashini? Yes. So
Vinegar.
vinegar is what acetic acid's common name is. So what you're going to do tomorrow is we're going to see if pH probes we're going to see if pH probes work, and you're going to do one titration with HCl and a pH probe, and let the LabQuest tell you this is the pH at this volume, this is the pH at this volume, this is the pH at this volume, and you should get a graph that looks something like what I made on the slide earlier. Then you're going to do it with bromothymol blue. Okay? You should find your equivalence point is at the same volume. Yes? Then you're gonna do it, the same stuff with the acetic acid and the NaOH. And because it's acetic acid and NaOH, we're not gonna use bromothymol blue in that second experiment. We're gonna use phenolphthalein. So take a few notes on phenolphthalein real quickly. PHENOLPHALEIN. Phenolphthalein. But it's pronounced phenolphthalein. The second ph is silent.
Phenolphthalein. That's
Phenolphthalein.
weird.
Phenol and then PHTHALEIN. LEIN.
Phenolphthalein.
All right, so phenolphthalein is colorless in an acid.
Is this an indicator?
This is an acid-base indicator. It is pink in a base, but it doesn't turn pink until a pH of about 8. Well, that happens to be about the pH at the equivalence point of a strong base and acetic acid. So my duty is to pick an acid-base indicator that's appropriate for what you're using. So I know that when you titrate acetic acid with sodium hydroxide, the pH at the equivalence point is going to be around 8. So then I think about which acid-base indicator is going to turn at about 8. Because I don't want bromothymol blue, it's going to turn where?
7.
At 7. Y'all following? Make sense? Kind of, sort of? Okay. So what I want you to do is make sure you read puberty. Make sure you read acid-base titration. I don't remember on what page of your lab manual it is, but read that lab before you walk in here tomorrow. Acid-base titration. Then what we will do Wednesday. Let me make sure before I lie to you. No, Wednesday is tomorrow. I keep thinking this is Monday. We will look at Unit 8, progress check. Let's talk about your progress check. So your multiple guess, some of you did fine on, some of you sucked on, one of you tore it up. I mean, 30 out of 33. Awesome. 30, I was just like, oh my gosh. Okay, so I'm going to share with you Thursday, the free response answers so that we can look at them together. And then I'm probably going to give you the Unit 8 multiple guess for homework on Thursday. Does that sound okay? And not do the free response unless you want to. Do you want to do, I'm giving you participation grades on this stuff. I'm not giving you grades based upon how you do. Y'all want to do the free response? Friday, maybe? So let's plan on that. And then I've got an old free response for you as well. So PCQ. And then PC8. Okay. Sound good? Next Thursday? I'm not here next Wednesday, Thursday, or Friday because I've got National JSHS. So y'all are working on practice problems with buffers, and then we're going to Zoom Thursday night to discuss what you've done Wednesday and Thursday. Remember, you had put in your calendar that we're zooming at like 7 o'clock, I think? Does that sound right? Okay. All right. So,
The week after weekdays can be the analytical type.
yeah, it can. It's just the titrate, you know, the concentration of. Anything else? All right, kiddos.